Hello, everyone, and welcome to tonight's stream. We are doing 3.9, and we are doing the Book of Proof, 3rd edition. This is by Richard Hammock, and you can download it in the video description. I have a physical copy. It's a nice book. I highly recommend getting a physical copy, but the download is free, and the book itself is in the Creative Commons. So yeah, let's do 3.9. It's page 104. I do the reading, and then I'm going to do the odds. The answer's in the back of the book, so if you look at the answers, you'll know before I do if I'm getting it right or wrong. All right. The division and pigeonhole principles. Our fundamental counting principle is called the division principle. Before discussing it, we need some notation. Given a number x, its floor... Alright, we're going to draw a floor. Okay, is rounded down to the nearest integer. Okay. Okay, so thus 10 divided by 4, which is 2.25. Okay, which is equal to 2. And wait a minute. Sorry, it's 2.5. Not 2.25. It's 2.5, so that's rounded down to 2, and 9.31 is 9. 7 is 7. And the ceiling, so this is the floor. And this is called ceiling. Rounded up to nearest integer. Okay. So then 10 over 4 ceiling is equal to 3. 9.31 is 10 and 7. Okay. The division principle is often illustrated by a simple situation involving pigeons. Imagine n pigeons that live in k pigeonholes or boxes. Okay. So we have n okay. Now and we're going to say possibly n is not equal to k. There could be less pigeonholes than there are pigeons. At night, all the pigeons fly into the boxes or pigeonholes. When this happens, some of the K boxes may contain more than one pigeon, and some may be empty. But no matter what, the average number of pigeons per box, n over K, and that's the average. Obviously, at least one of the boxes contains n or more pigeons if there are less boxes than there are pigeons, because not all the boxes can contain because not all boxes can contain fewer than the average number of pigeons per box. In other words, if you have 10 pigeons and 4 pigeonholes. Okay, you can't have on average, let's see here, 10 divided by 4, so that the average is 2.5. You can't have an average of less than that all around, right? Some boxes are you're gonna say some can have, I don't know, like one box, let's say box 1, box sub 1 can have, say, 3 pigeons. And then box sub 2 has 1. And then box sub 3 has 3 pigeons. And box sub 4 has also 3 pigeons. So, no matter how many pigeons you stick, you can't have an average per box. Like, if you were to put 9 pigeons in the one box, you still have to average them out. So, the average is spread, the density is spread out among the boxes, even though we're talking about whole numbers. You don't have half a pigeon in a box. But basically, the average, we see the average density spread out over the 4 boxes is 2.5. And depending upon whether you use floor or ceiling notation, the average could be set to be either 2 pigeons or 3 pigeons per box in terms of whole numbers. Okay, so we call this a division principle. Some call it the strong form of the pigeonhole principle. Some books. Okay, division principle is basically okay, n per k, say at least one box contains n per k or more objects. So basically what I was showing earlier, we had 3 pigeons per box, but at least one box is going to have at least 2.5 or more pigeons per box. Now, I could have put 9 pigeons in a box, but that would still hold. At least one of the boxes had more than 2.5 pigeons per box, basically. Or at least one box contains NRK floor or fewer objects. Okay. And we can say, here we go, we're going to continue on now. If n is greater than k, then n divided by k is greater than 1. So the ceiling of n divided by k is greater than 1. Which means at least one box has more than one object. And if n is less than k, then n divided by k is less than 1. So the floor of n divided by k is less than 1. Meaning at least one box is empty. Okay. Now, let's see here. Right. So yeah, suppose n objects are placed in k boxes. If n is greater than k, then at least one box contains more than one object. If n is less than k, at least one box is empty. That's the pigeonhole principle, basically. The pigeonhole principle is named for the scenario in which n pigeons fly into k pigeonholes, or boxes. If there are more pigeons than boxes, if n is greater than k, then some boxes gets more than one pigeon. And if there are fewer pigeons than boxes, at least one box must be empty. Like the multiplication, addition, and subtraction principles, the division and pigeonhole principles are intuitive and obvious, but they can prove things that are not obvious. The challenge is seeing where and how to apply them. Our examples will start simple and get progressively more complex. For an extremely simple application, notice that in any group of 13 people, at least 2 of them were born in the same month. This is assuming we use a Gregorian calendar, of course. Or similar calendars. Although this is obvious, it really does follow from the pigeonhole principle. Think of the 13 people as objects and put them each in a box that has their birth month. As there are more people than boxes, months, at least one box or month has 2 or more people in it. That means at least 2 of the 13 people were born in the same month. Further, for any group of 100 people, the division principle says that there is a month in which 10 divided by 12, or 100 divided by 12, which is equal to 9, or more people were born, rounded to the top. So, using the ceiling. It also guarantees a month in which the floor of 100 divided by 12, or 8 or fewer people were born. So basically, using this division principle, we could say, okay, 100 divided by 12, and if we want to know what the minimum of the max is, so what is the minimum of the max? In other words, what is the smallest, largest number that you can have? And that is the density can't be lower in at least one of the months than 8.3, which rounds to a 9 or more. So at least one of the months is guaranteed to have 9 or more people. Okay, and also, what is the minimum number? So what is the smallest possible outside of nothing, right? So can we have, so we go like this. We say 100. What is the smallest large number? In other words, you could say like there could be 1 or none, but how high can you go up of the small numbers, and you're guaranteed, in other words, that each month still has its full complement of people. Because you could say, well, you could have a month with only one person, but then it's not evenly spread out. We want to get an even feel for it. If you were to spread out people most evenly per month, what would be the smallest of the minimum density that you can have? And again, it's 8.3, which is approximately 8 or less. So again, spread out evenly, your minimum density would be 8 or less people per month, and your maximum density would be 9 or more. Again, we're trying to get an even spread. All right, and then pick 6 integers between 0 and 9, inclusive. So 0 and 9 are included. All right. Here's 2 of them. Okay. Imagine 5 boxes, each with marked okay. So we're gonna say, I just put spaces. We're gonna say 0, 9, 1, 8. We're trying to maintain our density, I guess. Here, we'll see where they're going with this. 3, 6, 4, 5. So as you can see, the numbers have a somewhat even density, and there's 2 per box. So everything we did here, we're trying to maintain an even density. Okay. For each number that was picked, put in the box having the number written on it. For example, if you picked 7, okay, so let's say 7. So that goes in that box. 2, 7. If we pick 2, it goes in this box, okay? As there are more numbers than boxes, the pigeonhole principle is that some box will have more than one number, hence 2 of the picked numbers in it. Those 2 numbers to sum up to 9. So basically, if you pick 6 numbers, so picking 6 numbers, some numbers that are going to have, because, all right, if we were to pick 6 numbers, right, and then we had only 5 boxes, that guarantees that 2 numbers will be in the same box, at least 2, because there's only 5 boxes. So if you go 1, 2, 3, 4, 5, you spread out per box. 1 is the odd man out. It has to join with a partner somewhere and share a box. Now, if you had 6 boxes and 6 numbers, that wouldn't be the case. We could have a minimum density of 1, but it's possible we would end up with some empty boxes. However, here we have a guarantee to have at least 1 box with 2. In other words, our ceiling density would have to be 2 or more. It's guaranteed. And of course, there's a minimum of at least 1 per box. Now, let's see here. Again, looking for an evenly spread density. Okay. A store has a gumball machine containing a large number of red, green, blue, and white gumballs. You get 1 gumball for each nickel you put in the machine. The store offers the following deal. You agree to buy some number of gumballs, and if 13 or more of them have the same color, you get $5. What is the fewest number of gumballs you need to buy to be 100% certain you will make money on the deal? Oh, this is a clever one. Okay. So we need 13 or more to have the same color, and there's 4 of them, right? So basically, we're gonna say n divided by 4 has to have a density of greater than or equal to 13. Okay, times 4 times 4. Okay, that's going to be n has to be greater than or equal to 52. Okay. So hold on a minute. Let me check to make sure I did that right. Hang on a minute. You know that you have 13 gumballs of the same color if n is greater than 12. So the ceiling of... Okay, so hold on a minute. You need 13 or more. So we just have to have 12 plus 12 plus 12 plus 1. I think that's how it's done. So, oh no, sorry. So we need a... provided the ceiling is greater than 13. You will know that you have 13. This happens if n divided by 4 is greater than 12. So once, because these are whole numbers, so we have if n divided by 4 is greater than 12, then we're in the money, right? Because the ceiling, because we're whole numbers, as long as we go... So we're going to multiply this by 4. So that's going to be 48. And then to make sure that we cross, because that's still 12. We're not above 12. We're at 12. So we have to add plus 1. That gives us a density of this right here. A ceiling density. Now, even if it's... Watch this. So 49 divided by 4... is 12.25, but the ceiling of it comes out to 13. And that's what we want, right? So the ceiling of 12 is still 12. And so 48 divided by 4, 49. I hope this makes some sense now. There we go. Okay, so that's how we need 49 gumballs to be in the money, statistically speaking. I mean, they could have rigged the machine and just, it could be like, there could be like all reds or something like that. But that's the basic idea. All right, good. Now, so now remember what our deal was. How much money are we going to actually make? So they're selling it at, what is it, a nickel? For each nickel. All right, so let's multiply that, and you get $5. So basically we have 13 or more. Same color, you get $5. There we go. So we bought 49 times 0.05. So that means we spent 2.45. So 49 times 0.05. Okay. And then we subtract that from 5. So minus $5, we made $2.55. Okay, nice. Of course, if we bought 48, we're not guaranteed that we're going to win. Technically, if you bought 13, you could technically win. I would say that would be your floor possibility, because the requirement is 13 or more of the same color. There's nothing that says you can't get the first 13 to be the same color. So technically, you could stop once you hit that number. You don't have to go all 49. But, you know, for the way the system's worked out here, we're trying to figure out where we're 100% certain, statistically speaking. Okay. Okay, and of course, another way to do this, you can go red plus green plus blue plus white is equal to the number, and the number divided by 4, and then we can just solve it that way. So basically, yeah. And then we needed. That's good. All right. All right. So then that would solve the same way. 9 points. Okay, here we go. This is an interesting one. So 9 random points. 3, 4, 5, 6, 7, 8, 9. And this is a length 1. This is a length 1. Okay. 9 points are placed in the right triangle. Show that 3 of these points form a triangle whose area is 1/8 square unit or less. Allow triangles with 0 area, in which case 3 points lie on a line. Okay. So basically an area of 1/8. So basically what we could do is this. We can go this way. So we have, there we go. So the area, again, is base times height divided, so triangle. So if you've forgotten, it's basically base times height divided by half. Because a square is base times height. So So that's a box. BH. And here we have BH and then half. All right. So there we go. So that hopefully it makes sense. So now we have 3 dots. We have 3 dots, 3 dots. There are how many? I'm sorry, there are 9 points total. So what is the minimum density? So we have 9, and we divided it by 4. So that means we have 2.5. And actually, that's not 2.5. That's 2.25. 2.25. And if we have 9/4, the ceiling of that is going to be 3. And the floor of that is going to be 2. So that means we're going to have at least one of each. We're going to have at least a 3 and at least a 2. And so basically we have over here, so we have 4 of them. So we're going to have, let's say this one's going to have 2 dots, 2 dots, 3 dots, and this is 2 dots. So let's see here, that's 2, 4, 6, 7, 8, 9. So 2 plus 2 plus 2 plus 3 is equal to 9. And that's how we know. Now, what is our area for our 3 triangle, this one right here? Okay, well, this is going to be of a base unit of length of 1 and a height of 1. Now it's half, so we have, now let's do it. We're going to say 0.5 times 0.5 divided by 2, and that's going to be 1.25. Okay, so that is, which is equal to, this is area of 1.2, which is equal to 1/8. So that's how we can do that, or less. Yeah, and basically that's how that example worked. Now, let's do some questions here. This is a fun one. Show that if 6 integers are chosen at random, at least 2 of them will have the same remainder when divided by 5. 6 integers, okay. All right. So integers, 1, 2, 4, 5, 6, 7, 8, 9, 10. So 10, and we're going to say slash 0. Not divided by 0. It could be 0 or 10. Actually, let's just go with 0 because we don't care about the whole thing. 0. There. And that applies to 10 and so forth. 6 integers are chosen. At least 2 of them will have the same remainder when divided by 5. Okay, well, let's see here. 0 and 5 are going to be 2. These will have the same remainder when divided by 5. I think 3, 6, and 9 should have the same remainder, I think. Let me see here. 6. Well, these are multiples. Well, let's just go down the number line. Okay. All right. So we need to group them. So if chosen with 6 integers, well, let's just do tens, right? So we're going to say 11 divided by 5, 2.2. 11 is equal to 2.2. 12 divided by 5 by 5 is 2. 2.4. And let's try 12. Let's try 14. And then 16. This is equal to 2.8. 16 divided by 5 is 3.2. Here we go. It has to do with the form of the fraction it'll take. I see. Okay. When we divide, dividing yields some whole remainder. Okay, so dividing some fifth some part, dividing dividing integers yields some remainder of 5. It can be, the fraction would be in the form of try it real quick here. Okay, 7 divided by 5 is equal to 1.4. 0.6. Number 5. 0.2, 0.4, 0.6, 0.8, or 0.0, or a whole number. So, because 5 could only be subdivided into 5 pieces, because 5 can only be subdivided into 5 pieces by a whole number. There we go. Therefore, dividing any 6 integers by 5 will yield at least 2 with the same remainder box. Okay, so I'm going to read this and I'm going to explain what everything means. Okay. Up. There we go. All right. Dividing whole numbers yields some remainder of 5 is 0.2, 0.4, 0.6, 0.8, or 0.0. So basically, whenever we have a whole number, say like, I don't know, like 13, right? We're going to divide it by 5. How many 5s can we get out of it? We can get 1 5 plus another 5 plus we can get 3/5 out of it. Okay, so there's 3 pieces of the 5 we're able to take out. Any number that's a whole number that we divide, we're going to have a remainder of nothing, or we're going to have 1/5, or 2/5, or 3/5, or 4/5. So there's only 5 potential outcomes that we can have, and we're picking 6 numbers. So by the pigeonhole principle, okay, say by pigeonhole principle, dividing whole numbers yields some remainder of 5, and I listed them because 5 can only be subdivided into 5 pieces by a whole number. Therefore, dividing any 6 integers by 5 will yield at least 1 with the same remainder. At least 2 with the same remainder. Box, it means end of proof. So when you put this at the end, it just means end of proof. And this is kind of how you do a proof. And I can just say this proof at the top. Okay. Let's go see how they wrote it. All right. Solution for them. Pick 6 integers, n sub 1 through n sub 6 at random. Imagine 5 boxes. Label the boxes box 0 through box 4. Each of the picked integers has a remainder when divided by 5, and the remainder is 0 through 4, just like I said. And then for each n1, let r1 be its remainder when divided by 5. Put n sub 1 into box remainder r sub 1. Now put 6 numbers into 5 boxes by the pigeonhole principle. One of the boxes has 2 or more numbers that you picked. These 2 numbers have the same remainder when divided by 5. So yeah, because a whole number could only subdivide 5 into one of 5 pieces. All right. Next. What is the fewest number of times you must roll a 6-sided die before you can be assured that 10 or more of the rolls resulted in the same number? Okay. Right. So, 10 or more rolls have the same number. So we need how many rolls do we need? So we have 1/6 times n is equal to rolls equals to 10 is it's greater than 10. Okay, so our ceiling has to be the ceiling of n has to be greater than 10 by any m remainder. So solving this times 6, which would be n has to be greater than 60 rolls. So would have to be n has to be 61 or more rolls to 61 rolls, let's say, takes 61 or more rolls to get or more rolls of the same number. We're going to say, assuming a 6-sided die Assuming a 6. Oh, they already said that. A 6-sided die has a 1/6 chance to roll any of 6 numbers. Okay. At least it doesn't say 10 or more rolls in a row. That would be an astronomical number. And the way to find out 10 or more in a row, we would have to multiply 1/6. I could say 10 or more in a row. I'm just adding a question. So we're going to say 1/6 times 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 1/6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or 1/6 to the 10th power, basically. Which would be, you would have to roll, it would take 1/6046676. So 1 in 60 million, basically, if you wanted to roll 10 or more in a row. But to get 6 or more of the same number, no order required, and that's going to be 61. This is a separate question I just threw out there for fun. By pigeonhole principle, rolling a dice 6 times gives you the 6 possible numbers, and 10 times 6 gives you, this is, wait a minute, here was the question again. Before you can be assured 10 or more. It's 60, not 61. 10 or more results in the same number. It gives you 10 more rolls of the same number. End of proof. A 6-sided dice has a 1/6 chance to roll any of 6 numbers. By pigeonhole principle, rolling a dice... Oh, what did I write here? This doesn't belong there. Rolling a dice 6 times gives you the 6 possible numbers, and 10 times 6 gives you 10 or more rolls of the same number. End of proof. Okay. All right. Okay. Hold on. I was not right on that. Let me see why. Okay. What is the fewest number of times you must roll a 6-sided dice before it can be assured 10 or more rolls resulted in the same number? Imagine 6 boxes labeled 1 through 6. Every time you roll a die, put it in a box. Each time you roll, each different number gets its own box, basically. N divided by 6 ceiling objects. This means you rolled n number of 6 ceiling times. We seek the smallest n for which n is greater than 6. Smallest n for which n is greater than 9. Well, okay, so why is it 9 though? N is greater than 9 is 54. Thus, the answer is N55. You need to roll the dice. Oh, right. Hold up. Right. Okay. Let me fix this. So, gives you the 6 possible numbers times 5. 10, a minute. We wanted the 9. So basically, because we're gonna round up, 9 gives you. We don't need to cover full density. We're not trying to carpet all of them over, just the one that we want. Okay, so 9 gives you more. Gives you 9 or more rolls of every number. Okay. 9 times 6 gives you 9 or more rolls of every number, which is equal to 54 rolls. Now, and then plus 1 more roll to get n over 6 rounded to, and we're going to round that to equal to 10. So, because we're rounding up, and then in this case, make sure that is greater than, and we need it, yeah, we're going to say greater than or equal to 10. And because 55 divided by 6 and 54 over 6 ceiling is equal to 9. 55 over 6 ceiling is equal to 10. Okay, so that's the thing. Technically, it's 9.166, which is small. Usually, when you think about rounding, you would end up rounding down. Anything less than 0.5, you round down. Above, you round up. That's how it's usually done. But in this case, we're using the ceiling and floor method. So even if it's over by 0.01, you know, you're over that mark. You're over the line. You're gonna get it rounded. So that's the trick. It's 55. Okay, cool. Now we have 5. Prove that any set of 7 distinct natural numbers contains a pair of numbers whose sum or difference is divisible by 10. Whose sum or difference is divisible by 10. Okay, so any 7 distinct natural numbers. Okay, any 7 any set of 7 contain a pair So that means you add it or you subtract it, and you're going to end up with a 0 on the end for any numbers. So any 7. If you take 10 and any 7 natural numbers, let's see, 10 minus 7 minus 6 minus 5 minus 4. I don't even know how that's supposed to. If you take it has to do with the ending parts of them. We have 1, 2, 3, 4, 5, 6, 7. That's because 8 is equal to 4 times 2. 9 is equal to 5. All right, hold on. Let me think about this for a minute. It has to get a 0 out of it, whose sum or difference is divisible by 10. This also has to do with remainders. Seven distinct natural contain a pair of numbers whose sum or difference is divisible by 10. Okay, and we don't know that we're picking the first 7. I'm just interested in their ending. So taking the first 7, just out of curiosity. 3 plus 7 is 10. 4 plus 6 is 10. But the negative, I can't get the negative to work. I can argue that any 7 whose sum or difference is divisible by 10. How would we prove it? I could say divisible by 5. Sure, I can prove that. So what if it was like the first 7 numbers? Let's see one more time. Prove that any set of 7 distinct natural numbers, I have them, contain a pair of numbers whose sum or difference is divisible by 10. Right? So, well, we can do the sum there and there. That's our sum. Now, what about difference? Yeah, I can't get that to work. 7 minus any of those numbers is going to give us an odd number or an even number, but it will not be divisible by 10. 6 divisible by 5 is minus 5, minus 4, minus 3, minus 2, minus 1. Again, it's a whole number. 5 minus 4, minus 3, minus 2, minus 1. 4 minus 3, minus 2, minus 1. 3 minus 2, minus 1. 2 minus 1. 1. No, it doesn't make sense. I don't even understand the question. By the way, when it comes to proofs, I don't even understand the question is a normal thing to say. All right, let's see how they did this. Because I can say, for example, that any number above 6 will inevitably repeat, resulting in even. Let's say, I'm going to do the first part at least. Any number There is okay, I would say 7 distinct numbers. And what is exactly is a distinct number? So what if it was like 11, 22, 33, 44, 55? Oh, well. Oh! I see now. I understand the question. It has to be sum or difference. So, in other words, it doesn't have to be both, but it can be one or the other. That I can do. Okay. So you can either create a system here where you can't get a difference, but then the result will be the sum. Or you can get a sum, but then you can't get the difference. Although you could have both. It could be one or the other or both, basically. Okay, having numbers plus small numbers. There are 5 numbers you can add. Numbers ending in 1, 2, 3, 4, or 5. You can add them. 10 is divisible by 2 and by 5. Thus, any numbers containing 2s and 5s. Okay. Let me see how they did this. Okay. Let S be a list of the 7 natural numbers. Say that all the numbers are bigger than the other. Okay, now thus the cardinality is A is 12. Okay, so okay. I see what they did. Okay. So basically we're going to say A1 minus 3, 1 minus 4, minus 5. Okay, so we're going to say A is equal to, we're going to create a set of numbers. A1 minus A2, comma, A1 minus A3, comma, A1 minus A4. Okay. Comma, A1 minus A5, comma, A1 minus A6, comma, A1 minus A7, comma, and then we're going to say A1 plus A2, comma, A1 plus A3, A1 plus A4, A1 plus A5, A1 plus A6, A1 plus A7. Now, and then we're going to say, okay, so that means, for example, Okay, and one more time in me. Okay, so 7 distinct natural numbers contain a pair of numbers. So basically we're saying, okay, there are, let's see here, 1, 2, 3, 4, 5, 6. There are 6. There are 12 now and 10 possible and numbers 0. We're gonna say 0 through 9 by pigeonhole principle. At least one divisible by 10. So basically, when you take those numbers, any 7 doesn't matter. It doesn't have to be 1 through 7. It could be like 99, 13, 21, whatever. Because these are whole numbers, there's going to be no fractions. So whether you add 2 numbers or subtract 2, you're going to end up a whole number on the end. And as we know, with whole numbers, there's 0 through 9. That it could be 0, it could be 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 different possibilities, but we have 12 numbers. So by the pigeonhole principle, every number is covered, and plus we start repeating numbers at that point. So that is how you do the proof. That's why they said specifically why you had 7. Notice why it wasn't 6. Because it was 6, then it would have been 1 through 6 added and 1 through 6 subtracted, so that would have been 10. You could still make a pigeonhole principle argument saying that there are 10 numbers and 10 outcomes by the pigeonhole principle. The number would have to repeat. So yeah, you can do that too. All right. This stuff is hard and unintuitive. I mean, maybe it was a little intuitive, but proofs are hard, and I couldn't figure out how to approach that one. But yeah, so when it comes to proofs, you have to there's no shame in saying I have no idea how this works. But you have to work through them. You have to eventually understand how it works. You don't have to solve everything by yourself. If you can't, ask your teacher or look at the answer. If it's the type of book here that, we could look at the answers. But you have to understand the process. So for example, I could repeat the process with different numbers now because I understand how it works. Anyways, that's the end of this chapter. We just have 3.10, the combinatorial proofs. And then it's part 2. I can't believe it. We're on page 108 next time. How wild is that? We covered so much ground. Anyways, I hope you enjoyed.